Hello and welcome to helpyourmath.com. In this video, we're going to look at solving exponential equations using the change of base strategy. So what is the change of base strategy? Well, what happens is we're going to take our exponential equations, and remember, if we have an exponential equation that's of the form b to the x equals y, we can always write it in logarithmic form as log base b of y equals x. So the base, argument, and exponent over there. Once it's written in this form, then we can use that change of base property that says if I have a logarithm, I can rewrite it to get a more consistent base, or a base that's found on a calculator. So I could rewrite it as log base 10 of b over log base 10 of a, or natural log of b over natural log of a. That's the log of the argument over the log of the base. And the reason we want to do this is because our calculators generally only have log base 10 and natural log, so you can choose which one you want to use. Okay, so just to review what this means, if we have 2 to the x equals 7, we could rewrite this exponential equation as a logarithmic equation. That would be log base 2 of 7 equals x. And now we have exactly what we see here. Log base 2 of 7 we can rewrite as log of the argument, and I'll use base 10 here, log of the argument, so log of 7, over log of the base, log of 2 equals x. Then you can plug this in your calculator. Make sure when you plug in your calculator that you close the parentheses on that numerator, because if you don't close the parentheses, then your log of 2 is also going to be part of the numerator. It's going to get very confused, and it's not going to give you the right answer. In the end, I end up with x is approximately equal to 2.807. Usually, if it's not indicated, just round to the nearest thousandth place or to the third decimal place. And does this make sense? So does 2 to the 2.807 really equal 7, or approximately 7? Since I rounded, there is room for error. Yeah, because 2 squared is 4, and 2 cubed is 8, and 7 is in between 4 and 8. So that makes sense. Seems reasonable that we end up with 2.807 for our final answer. In the next example, we want to make sure that that exponential term is by itself. We want to divide both sides by 3. This would give us 1/2 to the x is equal to 17. The reason we can't multiply here is order of operations says we must do the exponent first, and we can't do the exponent, so therefore we can't multiply. That kind of like blocks the order of operations from there. Now I have this in exponential form, I can rewrite it in logarithmic form. That's log base 1/2 of 17 is equal to x. Now that it looks like this, I can use the change of base, and this time I'll use the natural log just to switch it up. I can take the natural log of the argument and divide it by the natural log of the base, and that's going to give me an approximation for x. So when I do that in my calculator, log of natural log of 17 divided by natural log of 1/2, I end up with negative 4.087. So if we were to plug in negative 4.087 up here into this original equation, we should end up with an approximate answer of 51. It won't be exactly 51, or maybe it is. No, it won't be. But it'll be really, really close. Are there any restrictions on the values for x in this case, for the exponents? No, we don't have any restrictions on exponents. Let's look at a few more examples of applying the change of base property. Here we want to get rid of this coefficient of 4. We don't want to get rid of it. We just want to move it to the other side. So we'll divide both sides by 4. This gives me 5 to the x equals 9. I noticed that, usually it's good to check to see if you can use, if you can rewrite them as the same base, but we're not going to be able to write 9 as a base 5. So instead, we're going to put this in logarithmic form. That would be log base 5 of 9 is equal to x. And then once we have this, we can use that change of base property. I'll use my log base 10. That would be log of 9 over log of 5. It's always, always, always with change of base, it's always log of the argument over log of the base. Always, always, 100% of the time. And when we figure out this approximation, we see that x is approximately 1.365. And again, this makes sense. I'll skip the first line, but after we divide it by 4, it makes sense that it would be 5 to the 1.365, because 5 to the 1 is 5, and 5 squared is 25, and 9 is somewhere between 5 and 25. So the story checks. In this example, we want to make sure that 8 to the x is by itself. I'm going to subtract 15 from both sides. This gives me 8 to the x is equal to 27. Now that it's written like this, where we have just one base, one exponent, and one answer, we can convert it into logarithmic form. That would be log base 8 of 27 is equal to x. Now we can apply the change of base formula, so I will use this time natural log. That would be natural log of 27 divided by natural log of 8 is going to tell me an approximation for x. And so when we do this, let's keep in mind, like 8 to what power should be about 27? It should be 1 point something. And it is. It is 1.585 approximately, plus or minus. Okay, a few more examples of applying the change of base property. So here we have the base all by itself. The exponent has some stuff going on. There's nothing we can do about that. But we can put it immediately into logarithmic form. This would be log base 6 of 21/100 is equal to negative 4t. So we're going to clean this up first, and then we're going to worry about the fact that something's happening to t. I used ln last time, so I'll use log base 10 this time. Log base 10 of 21/100 divided by log base 10 of 6 gives me approximately, so plugging in, we have a small numerator, 21/100, and a bigger denominator, so I'm expecting this to be a negative. Yep. Negative 0.871, and again, this is just an approximation. So I get negative 0.871 is about equal to negative 4t. Now I want to get t totally by itself, so I'll divide both sides by negative 4. And so it depends what happens here. If you just keep in your calculator what it was exactly when you divided log of 21.21 by log of 6, you'll get one approximation, and if you just use this approximation here, it might be slightly different. I think in this case, the first 3 digits end up being the same either way, but just keep in mind there is going to be a little bit of error with these, and that's okay. I get t is approximately negative 0.218 when I divide both sides by 4. And our last example, we're looking at base e, and e has a coefficient. We're going to divide both sides by 1,000. Divide by 1,000. This gives us e to the negative 4x is equal to 125 thousandths, or 0.125. Now that I have it in exponential form, where I have my base, my exponent, and my argument, I can put this into logarithmic form. Now I said so I keep switching, right? Last time I used log base 10, so this time I'm actually using the natural log. And actually in the next video, we're going to do a different strategy entirely where we don't have to do the change of base property. And it kind of naturally occurs if I use natural log. So if I rewrite this using, oh, I'm sorry, I need to get this in logarithmic form. I'm getting ahead of myself here. I'm so excited about that. So this would be log base e of 0.125 is equal to negative 4x. Now, the point here is that this log base e is the same as the natural log. So we have the natural log of 0.125 equals negative 4x. Now here's the deal. When I go to rewrite this using the change of base property, if I use that natural log, it's like it's already there. In fact, we don't even have to use the change of base because this is already an expression that we can put in our calculator. So it's kind of nice how that worked out for us, that look, we're done here. And if you don't believe me and you leave it like this, you can use log base 10 if you want, but if you use natural log, it just naturally happens. If you leave it like this and you ignore the fact that log base e is the same as natural log, and then you did the natural log of 0.125 divided by the natural log of e, just kind of using that change of base property, well, this is equal to 1, because that's a identity. So either way, we're going to end up back here. We get to skip a step there. So it's kind of nice how that worked out. And the natural log of 0.125 is negative 2.079. So we have negative 2.709 is approximately equal to negative 4x. If we divide both sides by 4, we end up with 0.520 is our approximation for x. So this one's a little bit weird because the natural base is always a little bit weird, but hopefully it makes sense that log base e is the exact same thing. That's what ln stands for, is log base e. And then once you have natural log, that's a key on your calculator, you can just plug that right in, and we can not worry about this step here. But of course, if you do this step, that's totally fine. You'll still end up with the same answer. So this has been looking at the change of base property. In the next video, we're going to look at examples of applying the natural log, of looking at the natural base and solving with the natural base. Thank you for stopping by.